Hi, I'm Jon Guthrie. Say
Hi,
hello,
and I
Steve.
am Steve Hoye, and we're the analytics for energy guys. We'd like to start off with a business premise, and that is you are working hard in your everyday office there as an oil and gas company, and you have been approached with an opportunity to purchase assets in the Permian Basin. These assets happen to be in Glasscock County in the Midland Basin. And there are two properties to this opportunity that are key for us here in our little demonstration. First one is that it's fairly large. It has to do with a producing field that exists already. There are a fair number of wells in this opportunity. And the second part of it is that you don't have much time. We don't have 6 months to review the opportunity and cross all the T's and dot all the I's. We need an answer here in a very short period of time. So what our strategy is going to be is it's a two-pronged strategy. First of all, we're going to look at these wells very quickly and evaluate them in the A4E tool, which does a whole series of different operations, which will allow us to forecast these wells using sophisticated autocasting. The second piece is then, because this is such a big opportunity, we're going to need to get economics in a system of record, which is going to be PHDwin version 3. So together, these two things are going to give us the answer and help us make a decision on this large opportunity in a very short period of time. That's our goal. So as we continue this demo, and we're going to take you through all this and show you how this can work.
Thanks, Steve. So we'll kick off by showing you some of the A4E tools and giving an overview of what we'll be using as we move through the demo. So as I said, we've got QA and QC, and we'll show some of that at the end of this workflow on the way back from PHDwin. The well spacing, we'll show some of that. Production review, looking at the wells that we want to include in our well set. Doing our probabilistic forecasts of thousands of wells with A4E, Markov chain Monte Carlo. Diagnostic plots of forecast production, plus operator comparison. Normalization of the well profiles using multiple completion attributes. And building and returning A4E type well profiles to PHDwin to project the economics. So over to you, Steve.
Very good. So to set the stage, A4E is a Spotfire based tools. So hopefully some of you or many of you on board here are familiar with Spotfire. It's a flexible, very powerful analytics engine that allows us not only to do calculations and computations inside it, but it also has very flexible visualization and selection capabilities, which you will see here. To start this, we obviously have a database that has wells included in the Permian Basin, and we quickly need to be able to push away all the stuff that's not a part of this deal that we're evaluating right now in Glasscock County. So I think Jon is going to start here, and we can localize ourselves down to the fields that are represented here. You can see there's a thing called a tree map. And Jon has selected in Spotfire the field. He wants to see the fields represented here, the number of wells proportional to the size of these tiles. Jon's going to go down here to Garden City South, and we're going to restrict ourselves to the wells in that field. Now, it turns out the AOI is a subset of the wells in this field and owned by a particular operator. And so we are going to, you can now see that Jon has selected Garden City South. You can see the outlines of Glasscock County in these visualizations centered. And the AOI that we're looking at are actually the wells that you can see kind of scattered in the middle. And Jon is going to put a lasso around those wells. So here in Spotfire, it's just that easy to select a group of wells that are a part of an AOI. And those are the wells that represent the hypothetical deal that we're evaluating right now. So given that Jon can now select those wells, we now have the opportunity to look at some of the production characteristics of these wells by reviewing the production curves that are there. So Jon's we've gone to the next page in the A4E workflow, and we're now looking at the characteristics of these wells. Jon can highlight the oil wells in this particular field. And, I think some of the interesting things that we can see from this are, first of all, what are we looking at? You can see in the lower left chart, you can see a log rate versus time. And you can see that, well, you're looking at wells here that will IP on the average somewhere under 100 barrels per day. You can also see the average decline over time. On the cum over time plot that you see in the lower right, we can also see that this is a fairly mature field. In the later part of these curves, you can see that they flatten out, meaning that much of the production has already been realized from these wells. There is one well specifically that is quite prolific and still on the upswing. That may be a well of interest as we evaluate further. What Jon can do after we kind of get a rough sense of this is Jon can come over to the spark lines on the left. That's where he is now. And you can see little representations of the production curve for each individual well. And we can zoom in on any specific well that we'd like and get some sense of, from an isolated standpoint, which wells are which, right? We can also, at this point then, once we've looked at the column that has the number of months of production, this table is actually sorted in descending order from the highest number of months of production available in the database to the lowest. Jon's going to mark these wells. In Spotfire, you simply drag your mouse click over whatever wells you'd like to select. He has selected all of the wells that we lassoed in the previous step. And these wells, we can now create a well set that will represent the starting point, the foundation for any further analytics we do, including the forecasting step that we're about to do. So Jon is going to come down after marking these wells. You can see them in yellow. It's going to come down to the icon that says new well set, and we will actually push that button and create a new well set here in Spotfire. That is a kind of an overview of what it looks like to select a set of wells that we intend to evaluate here in our hypothetical exercise here. So the next and maybe the most important step in our evaluation using the A4E tool is the ability to autocast using the decline data, production records from the database, to autocast or forecast what we believe the future potential of these wells is, both oil and gas. What Jon has done, we've moved over to a page called DCA, or Decline Curve Analysis. Jon has marked all the wells that you can see in yellow here, and we've set the parameters for the autocaster, which you can see down here in the lower left. And once those parameters are set, Jon went ahead and clicked on the gears that you see down at the bottom there, which actually ran the autocaster. We get very good performance on this autocaster. So for the 30 plus wells that we're working on right now, it simply takes a few seconds to be able to get that forecast done. Well, what you're looking at here, because Jon's got all these wells marked, is you're looking at the results. They're trellised in the upper right, the large production plots that you see here, with the autocast decline curves fit showing over the top of these individual production records. And Jon's got these all marked, so we could simply kind of scroll our way through these to kind of get a sense of, what the autocaster did. Now, what we want to do is highlight some of the capabilities of this tool. First of all, we have an outlier detection tool, which automatically identifies production records as outliers, and they're ignored in the autocasting process, or the outlier detection algorithm. Here you can see that the points, the production records that are actually marked in red for gas, green for oil, that when you see these crosses or these X's here, that these are basically identified as outliers. We can adjust or tune the performance of this outlier detection to match the data that we're dealing with, but you can see it's very effective in eliminating some of these production records that we really don't want to consider when we start looking at these decline curves. Secondly, there's an algorithm called a start-stop algorithm. So our tool automatically determines when there are interruptions or changes in the decline curve characteristics and attempts to forecast only the latest segment of production when there are distinct segments between these. Jon is going to highlight a couple wells here. This is the Bearcat 1505. We can look at the Bearcat 1505H. And if you'll notice, this was the initial pass of the autocaster, and you'll notice that there's a very distinct drop here. We don't know why this occurred. We could go back to the spacing and determine whether or not there's a frac hit that affected this particular well. But in any case, we don't really like the way the autocaster fit this. And we can tune the parameters of the start-stop algorithm to actually detect, using the plot that you see below here called a ratio plot, what threshold would be required to detect this change. And by adjusting the parameters that Jon has set over here in the lower left for the autocaster, we can adjust that and do a quick recalculation for any wells that we think need adjustments. Jon can append the new AutoCast versions into the base set that we did initially just now, and we get a new result based on that updated start-stop threshold. So Jon can show us both. This is the old version, and now we have the newer version just below that. Notice that now the fit that you see on that second well for oil exactly corresponds. It's so good that it's hard to see it here, actually, overlaying the production records. But this forecast we're much happier with. It does reflect this second stage of the well's production. And so this will highlight for you the capability that we have to very quickly tune some of the fitting that we do using the autocaster to get results that we're happy with. Finally, we're going to go over to a diagnostics page. This is the MC page, and highlight a little bit about what Markov chain Monte Carlo decline curve fitting looks like. So Jon can mark all the wells here, and what you'll find is that for every well, this Markov chain process generates thousands, or it can generate thousands of different decline curves, all of which describe the data, the noisy production records, in an equivalent way. And what it's basically therefore showing you are the error bars around the ARPS parameters that define the decline curve or curves that fit the noisy production. So you're seeing, for instance, in the upper left here, or in the center left, you're seeing a cross plot that's showing you all of the candidate decline curves for each of the 30 plus wells that we have in our data set here. And these little clouds represent different decline curves with different IPs, which are along the horizontal axis, and different initial decline rates, which are along the vertical axis here. And the relationship between those two things, and the fact that there is a cloud instead of a single point. So this is telling us what we all know, which is a single decline curve result in an autocasting algorithm is insufficient to really give a sense of what the uncertainty is in the decline parameters, and therefore in the EURs that we get. So using Markov chain Monte Carlo techniques, we now get uncertainty measurements or error bars around the various parameters. Jon's going to highlight a single well here, the driver 43-2H. And if we highlight that well, it'll basically, we can go from looking at a cloud of all the well parameters to a single well. So for a specific well, I want you to note that we have more than 1,000 different decline curves represented here. We could show them in different ways, including the histograms that you see as a center vertical strip here in the visualization space. These are showing you the uncertainties, the different fitted decline curves, and the uncertainty in the initial rates, in the initial declines. The B parameter is shown here in the lowest one of these charts. And finally, the EUR and the histogram that's associated with that EUR is shown here in the lower right. And so this is an eye opener, right? For noisy production records, which you see here in the, in the production and fit decline curve chart here in the lower part, you can see that the EUR could be anywhere from, at the upper end of this scale, 118,000 barrels down to, at a lower level in the less than 100,000 barrels of oil. So you're seeing what the most likely tendency is for the EURs. You're also seeing the P10 and the P90 values for EUR on this chart. So we're proud of the autocasting capability here. This happens in seconds. And not only do you get a decline curve, which we think represents a best fit, but you're getting a whole family of decline curves. One last point, or one other point that we can make. John is going to switch on the what we call the burn-in, and this will give you the opportunity to see, if you look at this little in the upper right, you're looking at a chart, and what we were looking at previously is the head, or this collection of points that you see in the upper right. This is once the machine learning algorithm associated with Markov chain Monte Carlo has learned the natural variation that's possible in explaining these production records. But if you look at the tail of this cluster that you see, which the tail extends from the lower left on up, you're actually watching the machine learning algorithm learn what variations in these different ARPS model parameters best explain the data, and it systematically moves toward a space that represents, therefore, the natural variation that can be explained by the noise in the production records. So Markov chain Monte Carlo, we believe, is a powerful approach to decline curve analysis, and it's superior in its ability to define not only what the best ARPS parameters are, but in showing you the error bars around those parameters.
While we're talking about diagnostics, let's take a look at some other diagnostic screens that we have in the A4E workflow. We have EUR diagnostics, 2 pages associated with that. Second page has a map, the curves, comparison, and scatter plot, all controlled by drop downs for color, size, and shape by. Bar chart similar. Pick the attributes you want to look at and the aggregation that you want to use. And for the scatter plot, similar in terms of being able to configure the x-axis, y-axis, color by, shape by, and size by of any of the attributes that you have calculated within the workflow. And there's a third page, statistics page, where we can do operator comparisons. The mean is calculated based on the attributes selected, and a ratio calculated of where the mean for this attribute sits overall against the operator. So for all operators, it's sitting at 1 at the moment, but if we picked an operator, we can see that for these attributes, they're above the mean. And we can look at wells within the well set by marking them in this sort of fashion. So let's see how we might use this. Here we are in the first EUR diagnostics page. So we have histograms for the EUR oil, EUR gas, and stacked bar charts showing the prod oil and the remaining oil for both oil and gas. So on our histogram for oil, we could look at the high end here of the histogram, and this is showing us a bare cap well at the high end, okay, where it sits relative to the other wells. And we could go to the second page here and say, well, where's that on the map? So it's sitting here. So what about the wells that are sitting around it? Let's take a look at them and see what their curves look like. And also where they sit. Obviously, these are all wells and they're sitting lighted in the scatter plot. So we've got these 5 wells selected. But if we wanted to, we could go and move to this area and see where they sit. Again, these are scatter plot here. They're sort of sitting around the middle here, comparing EUR oil against the remaining oil. And going back to the first diagnostics page, then we can see that they're not at the top, but they're towards the top of all the wells that we have on our well set and sitting in the median area. Finally, we've got a page of statistics, as we said, where we're comparing against the mean for various operators. So we could change the attribute that we're wanting to do the comparison against and see where that sits against all of the operators. So we can set the attributes, we can set the vintage. Maybe we want to change this to be looking by operator as well. And this one. And then we can choose off our well selection list, or we can do a comparison by operator. So see where Conical they're sitting ratio wise 0.42 of the mean for all the wells in our well set, and Vital's just above the mean for these attributes in the well set. So overall, some pretty powerful insights that we can get going through these diagnostics pages. So back to you, Steve, to walk us through normalization.
John has done is he's got all these wells and he's pressed a button there in the text box there under controls. And that what that button did is it generated a correlation, a measurement of the relationship between the EUR, the oil EURs, and all the numeric header columns that are available in the database. So you're looking at a tornado chart in the center there that's basically showing us the correlation coefficients, right? So you can see from the top, it's a tornado chart, right? The top is showing us positive correlations, and we move all the way down to negative correlations, right? Strong negative relationships. Those that are statistically insignificant are shown in black, right? But there's a lot of relationships here in these wells that tend to highlight. What we want to do, let's say if we wanted to do a conventional normalization, is normalize out the lateral length. That's one of the header values that we have in the columns here. John could turn around and mark the lateral length in this tornado chart. And he can go ahead then and compute the normalization, therefore, this simply normalizes out the lateral length. We can look at the scatter chart that you see in the center right of the screen here, and that's showing us the relationship between EUR, the oil EUR, and the lateral length. And you can see that there's a linear regression that's associated with this. And we could go ahead and normalize out a type curve at any of the sampled lateral lengths that are available to us here in the database. Now, what we'd like to highlight is the ability to actually normalize out any of the header parameters simultaneously. So from looking at the lateral length chart that you see here, there is a fair scatter in the lower lateral lengths up and down, that the EURs are very uncertain, and that clearly the relationship with lateral length doesn't completely explain, doesn't even very well explain some of these EURs that are associated with small lateral lengths. We have wells here that are more productive at very small lateral lengths than wells that their productivity is less at some very large lateral lengths. So what we'd like to do then is kind of highlight the ability to normalize out simultaneously any of the numeric header column values that are represented in this tornado chart we just looked at. So John, let's just for fun, let's assume that the total fluid first treatment is also an important parameter. You can see that it's got a higher correlation coefficient than does the lateral length. And so we're going to add that, I guess, total fluid first treatment. We're going to add that as a normalization parameter. And if we could go look at the field itself in map view and conclude that the latitude, right, the bottom hole latitude is also a parameter that is directly related. What that means is that this tool has identified that the northernmost wells, the ones with higher latitudes, are actually more productive. So using these three parameters, we're going to turn around and calculate a normalization using principal components and some other fairly sophisticated mathematics to generate a normalization function which accounts for all three of these values. Notice that we've got a little better scatter of the scatter plot that you see here, that this is a more effective characterization that we can use to normalize these data. And we're going to go ahead and use this. What we need to do based on this is identify a single well as a datum well. This will be the well against which these header parameters will be normalized. And you can see it now highlighted in green in the lower left. And we will have the option to use this normalization and use the datum well that John just identified as a datum in the normalization that we're about to do when we do the type curves. And notice that this well has a lateral length that's in the 7,000 foot neighborhood. That may be ideal. This may be close to the completion parameters that we might anticipate if we were going to drill subsequent wells in this field. Good. So John has navigated us to the type well profile page. And since we've completed a normalization that we're happy with, we're now in a condition to make some type well profiles. Very simply, this page is very simple to operate. John has marked all the wells that you can see in the red marking in the upper left table there. He's also got a map, which is up in the upper central part, which he just lassoed. That map, he set the contours for this map at EUR for oil in the controls that you see center left. We could mark wells that we wanted to include or exclude from this type well profile by simply lassoing them, like what John is doing here, right? So Spotfire provides multiple wonderful ways for us to include and exclude wells from this type well profile that might cater to our needs very specifically in terms of the evaluation that we're doing here. So what we intend to do here is generate two type well profiles, one using all the wells with no normalization, and another type well profile with all the wells that includes the normalization that we just configured in the previous page. The operation, as I said, is very easy. If John can open up he's got the type well model controls opened up in the accordion where he's pointing right now. We simply determine whether or not we want to apply the normalization. That's basically just a drop down. We can determine how we want to aggregate the production records. We've determined p hat, which is a kind of a Swanson's mean of the time slice data production records. And all we really have to do is define what the ID looks like for this type well. John's put in here, these will be normalized 34 wells. And we can put in some sort of a comment, which you can see down in the lower left of the control screen there, to kind of mark or help us remember how we selected the wells and how we can calculate the type well profile. In the end, though, all John did was click on the Generate Type Well Profile button, and every time he clicks that button, he generates a type well. In the case of this exercise, he went ahead and generated a type well with no normalization. He simply clicked on the Apply Normalization button above that and changed it to yes and generated the second type well profile once again just by clicking the button. So a very simple, in a minute or two, John could generate it. He went ahead and generated these two type well profiles, which you can see now listed in the table below. So we can cut to the chase here and take a look at both of these type well profiles, one normalized, one not normalized. You can see in the visualization, the little thumbnail down there, the two decline curves and the resulting fit type well profile. John's going to maximize that window. And this, as you can see, the aggregation of the 30 plus wells results in a fairly smooth, well-behaved, relatively well-behaved data production records profile that you see here for both the normalized and unnormalized wells. By the headings on these two charts, you can see that the top pair are not normalized. The bottom pair are indeed normalized. The differences are subtle, but if you look, for instance, at the maximum production on the oil curves, you can see that for the unnormalized record there, just the second production record is right about at 300 barrels a day. And you can see that in the normalized version, which actually extended out to some of the more aggressive, larger lateral lengths and larger completions for the total fluid and so on and so forth, and the more northern part of the field, that the maximum production record that you see over there, the second one, in the lower or normalized data set, approaches 400 barrels a day as a maximum there. Notice as well that the crossover point where the oil goes below 10 barrels a day on the unnormalized is about 8 years or so in the future, whereas with the type curve that has been normalized, you can see that the crossover point with 10 barrels a day is somewhere between 10 and 11 years. So this is kind of a indication or an exercise that shows you how easy it is for you to generate type well profiles, how flexible it is to be able to change those type well profiles and account for different items. And in the end, these are the well profiles that we intend to send over to PhDwin, where we can go ahead and do economic analysis. So what we're looking at now is the spacing module. And because we didn't have spacing data for the Glasscock County wells that we've been using in the well set, we're using a surrogate here, which is over to the west in Midland County, just to kind of demonstrate the capability. We're just going to spend a minute on this and touch at it at a high level, but we have highlighted, or we've calculated spacing for a whole series of wells here, which you can see in the map. And what you're looking at in the upper visualizations is a cross section that shows how the wells penetrate a cross section that's kind of orthogonal to the grain or the direction of the laterals. In the left or in the center upper chart, John has highlighted a subset of the wells. You can see that they're colored by operator, and he's highlighted the wells over to the east, which are operated by Vital Energy. And if you look to the right, you can see a gun barrel plot, which is showing us in cross section the distances in feet, both vertically and horizontally, between the different well bores as they penetrate this cross section that we've generated orthogonal to the laterals. In the lower or in the center, you can see a thing that looks like a target. And what's that showing us is for the marked wells, it's showing you the proximity in feet, both vertically and horizontally, of the wellbore directional survey points to every other directional survey point, with the reference points in these marked wells being at the center of this coordinate system, which is 0, 0. So you're looking at the relative spatial relationships between wells nearby and each of the wells themselves. And you get a sense of how close some of these wells are to one another. By little clusters, you might be able to see spacing parameters that are important or that were used in the fields. And it also might give you an opportunity to look for wells that basically don't have nearby production and that maybe represent some future potential. Finally, or in the lower right, just to kind of get a sense of the whole picture, John has got a three-dimensional wellbore plot. And John may maximize this, and you can get a feel spatially for all of the survey points that are being used in this analysis. The ones that John marked by Vital Energy are shown in red, and those that are unmarked are you can see a kind of a more washed out color looking in the green there. So all in all, what this allows us to do, and we can reference back to the well where we did the start stop, it looked like there might have been a frac hit. We would go in and find that well in this, mark its neighbors, and then try to determine very quickly whether or not it's likely that there was some sort of a frac hit based on the analysis that we've done.
Thanks, Steve. We have our forecasts of our 34 Glasscock wells plus 2 type wells. And as we said at the start, we're going to move these to the PhDwin economics engine. Now, the A4E template does have an economics page here. Standard, I would say, economic type calculations and forecasts. In our case, we're going to use the power of the PhDwin economics engine to get a systems of record style forecast from there. So to do that, we go to our PhDwin export page. We select the wells that we want to export. Here we've got the 2 type wells at the bottom here and the others. So I'm just going to select them all. And we can see that we have 3 windows here. The cases, which is the information from the well headers, right, with all the columns from there. The production for both the actual production and the forecast production for all the wells and the type wells, and the forecast itself, the definitions of the curves to go into PhDwin version 3. So now I'll stick on my PhDwin hat and move across to there. So to export these files to PhDwin, we do an export of the visualization of Microsoft Excel for each of the tables here. And we can see I've got one for cases, the production, and the forecast. We then can change these files to CSV from Excel and import them to PHDwin. So here we are in PHDwin version 3, a tool you're probably more familiar with for its power on the economics than I am. We've brought the A4E files in here by just using the import option and using the unique ID, adding new cases for the cases from A4E and mapping the data, set up a map for it for the well headers and map the columns appropriately. And then did the import. Then similarly for the production, imported the production files here. It didn't use the unique ID this time, used the retrieval code and mapped the data. And again, there was a mapping for this. And then finally pulling in the forecasts from A4E. Then the layout for that was for the forecast. The mapping is so on. So the unique ID was on the end here, the retrieval code. So that gave me the cases imported. If I change the view here to the standard view, then I've imported the cases, which we can see here. We have the production, we have the forecasts from A4E. And the last thing I had to do was I just added some prices so that I could run some economics. In this particular case, I didn't create any price decks for expenses or custom models or ownership or investments. I just did a very simple price deck and ran the model. So we can see the curves coming in here. Including we've got the two type curves at the bottom, the normalized one and the non-normalized one. So let's now move back to see how we can import the results from our economics run back into the A4E PHDwin Reports template. So to send all the cases back to Spotfire, we run the Spotfire export. I've set it for cases and summaries, and we select all the cases and run the report. When the report is run, it shows a completion window showing that it's exported the Spotfire case tables, Spotfire ID codes, monthly MS, monthly production, and the one line. The latest PHDwin A4E reports template provides the foundation for creating a full analysis of your PHDwin data. To refresh the data in the analysis, you can click the lightning connector there. Will refresh the data from your Spotfire export within PHDwin. Typically, once you've set up your interface here for the probit metrics, for the values you want to include in your probit metric, that would be a one-time setup for your analysis. And you can see the values that I'm passing into the probit data function. Also, this is a one-time setup as well for your interface to PHDwin for the well names, the UWIs, and the latitude and longitude for use on the maps within this template. So with the data set up, typically you would click the run the probit once you've refreshed the data, and then you're ready to look at the pages. So there's a number of pages within this tool. So here we can see that we've imported our 36 wells here over 2 fields. And we've got various filters and so on set on the left. But you can customize this template to your own analysis workflows if you wish. There's a reports and summary page here where you can set the variable that you want to evaluate, gross gas, gross oil, and do you want to look at it by reservoir or case name maybe, and so on, or case name or possibly operator maybe, and it's flexible there. So this can be configured for your own use. Then we have a reporting table down here by case name, and you can add or take away columns from here to suit your analysis needs. There's a well scenario page. So if you've run multiple scenarios against these wells, then you can take a look at the results from that, either by one well, setting up the table columns, table selector columns as for previous, looking at it over the months, dates and months. So set the columns you want to see and roll that forward in that fashion. or look at individual wells as we go through here, or pick a well off the map. Then on well performance, we can see the actual production and the forecast for each well. So we could pick a well, see the production and the forecast that was generated for it with a cash flow waterfall on the right. Although in this particular case, as I only generated prices, there's no back out of the operating costs, expenses, and so on. There's a simple probit review here. Again, this is similar to the one that we saw earlier in the A4E forecasting and valuations template. Set the filters here and the attributes and color buys to do a comparison of the different attributes that we've pulled through from our PHDwin data. There's a data relationships page, and then we move to the probit perspective, where from the map you can pick the values that we pushed into the probit calculation, and we can see from the probits where these wells sit in relation to one another in terms of P10 to P90, and then which dimensions do we want? Do we want it by operator name or filter by operator as we go to the Vital wells in this case? And then we have statistics generated. So a full range of statistics in terms of the means, descriptive stats, and different stats types. So the analog stats, color coded, the applied curve fits, and the descriptive stats for the wells selected. Then there's some heat maps to finish with, similar again to the A4E forecasting template that you can select the attribute and it'll generate the heat map and contour plots for that. And then again, a template page similar to the one within the A4E forecasting template where you can set the map parameters, the bar chart entries, and the scatter plot and the aggregation. So that's the A4E PHDwin Reports template. Again, this can be the basis for building your own Spotfire visualizations to analyze your PHDwin economics.
Wanted to thank you all for your attention here and your attendance at PHDwin Week. We are thrilled to be partners with the folks at PHDwin. Hopefully that you saw from our talk that the powerful combination of tools with different specialties results in things that are made to order for businesses. In the exercise we did, I hope you can see that by using the A4E tool to quickly select and evaluate, forecast wells, generate type well profiles, that the power there in the speed and the sophistication of the analysis, it also allowed us then to generate wells which went back into PHDwin. The power there to be able to generate the economics of record that we require for our board of directors on this particular exercise are key. And then the ability to seamlessly take the data from the economic analyses that we saw in PHDwin and run those back into Spotfire to be able to do visual analytics on the subsequent data there represents a kind of a best-in-class workflow as we estimated here. So thanks so much. We thank the folks from PHDwin for the opportunity to be their partner. We value the partnership greatly, and we'll look forward to answering any questions that you might have about the workflow.
Thank you all.